So today's lesson is Unit 3, Functions, Lesson 5. We are comparing the properties of functions. So our learning goals today, when we are finished with this lesson, you should be able to identify the slope or the rate of change and the y-intercept or the initial value of a function, whether it is presented as a graph, a table of values, or an equation. You also should be able to compare the slopes and the y-intercepts of various linear functions and answer questions based on these comparisons. When we use the term compare, we think in terms of smallest to largest, least to greatest. Maybe we see phrases like, is it a better value? So we're going to be able to answer questions like that. Let's start off with our vocabulary. Our first vocabulary word today is a linear function. And really, this isn't a vocabulary term. It's not new to you. You've seen this several times before. A linear function makes a graph that is a straight line. The forms of linear equations that we have worked with so far are slope-intercept form, which looks like this, y equals mx plus b. And we've done some graphing in standard form, ax plus by equals c. A distance time graph, that's our next vocabulary word, distance time graph, is just a graph. And you guessed it, it's going to compare the change in the y-axis, which is the distance, to the change in the x-axis, which is time. The x-axis is always labeled as, yes, you're right, always labeled as time. Why? Not because Mrs. Bischoff told you. Why is the x-axis always labeled as time? Well, if you think back to when we learned about independent and dependent variables, remember that the independent variable is always the x-axis. The dependent variable is always the y-axis. And time does not depend on anything, whereas how far you go depends on how long you're traveling, right? So the distance depends on the time. Time is always independent. Well, let's try that again. Time is always independent. So that's why it goes on the x-axis. Because the x-axis represents the independent variable. Okay? All right, let's do some examples. First example. So our first example asks us to look at the three linear functions below. You'll notice that the first one is a table of values, the second one is a graph, and the third one is an equation. And this equation is written in the form y equals mx plus b. Remember that m is my slope and b is my y-intercept. All right, so we're going to look at the three functions below, and we are going to compare the functions in terms of their slope, listed from least to greatest, and in terms of their y-intercept. So the first thing that we need to do is calculate the slope and the y-intercept from each function. So our first function, function A, remember when I want to calculate slope from a table, I just try to find the change between the two values. So to go from a positive 2 to a negative 2, it looks like I subtract 4. Negative 2 to negative 6 is also minus 4. Negative 6 to negative 10 is minus 4. Let's look at the change in the x-axis. 9 to 3 is a minus 6. This is also minus 6 and minus 6. So my slope, my change in y, negative 4, over my change in x, reduces to a negative divided by a negative is a positive, reduces to 2/3. Now the y-intercept is interesting because we know that a graph crosses the y-axis when x equals, yes, you're right, 0, when x equals 0. I notice that I don't have any ordered pair where x equals 0. However, if I were to find the distance from these 2 points is 6, so half of that would be 3, which would put a 0 right there, and the distance between these 2 points is 4, and half of that would be 2, which would make this negative 4. So the y-intercept happens at the ordered pair 0, negative 4. So it crosses the y-axis at negative 4. The next graph, or the next function is a graph. I am just going to count my slope. It looks like I go up 1, 2, 3, 4, 5, 6, and I run to the right 1, 2, 3 units. 6 over 3 equals 2. So my slope is 2. And my y-intercept, I see that I cross the y-axis at 6. The last function is an equation. The slope is the number attached to the x variable when it's solved in terms of y equals mx plus b. So my slope is 3/4 and my y-intercept is 4. So if I were to compare these functions in terms of least to greatest by looking at their slope, the smallest slope is function a with 2/3, then function c with a slope of 3/4, and lastly function b with a slope of 2. If I were to compare these functions again in terms of least to greatest by looking at their y-intercepts, I would see that the smallest y-intercept is negative 4. That comes from function a. The next is c at 4, and then the last one is 6 for function b. Alrighty. So now I want to look at some examples in terms of comparing. And here we're going to talk a little bit about distance. So if I drove my car at a constant rate of 70 miles per hour for 3 hours, how many miles did I drive? So how would you think about that? If I was driving for 70 miles every hour and I drove for 3 hours, how far did I go? Well, hopefully you're thinking that you're going to take the miles that you drove multiplied by the amount of time that you drove, and you find out that 70 times 3 is 210. So the total miles, or the distance, is 210 miles. So could you write an equation for distance, d, using rate and time? Well, let's see. The total distance that I drove was I took the rate, 70 miles per hour, and I multiplied it by the time. So this equation right here, d equals rt, is the formula for distance. This is how we find distance. The rate, R, is typically our speed. It tells us how fast we're going. Time can be in seconds or minutes or hours. This current example has our time in hours. We multiply the rate by the time to get the distance. So example number 3 says that Jeff drove at a constant rate of 75 miles. Jeff drove at a constant rate of 75 miles per hour. So in our next example, Jeff drives at a constant rate of 75 miles per hour, while Debbie's rate is modeled by the graph. So when I look at the graph, I see that in 10 minutes, Debbie has driven 10 miles. Jeff drove at a constant rate of 75 miles per hour, while Debbie's rate is modeled by the graph. When I look at the graph, I see that in 10 miles, Debbie was able to travel 10 miles in 10 minutes, which means that she's traveling 1 mile every minute. So how could I put that in terms of miles per hour? Well, let's see. There are 60 minutes in an hour. So if I multiply both the top and the bottom by 60, I see that Debbie is traveling at 60 miles per hour. So the first question is, who is going faster? What does it mean to go faster in terms of a graph? Well, when you think about going faster in terms of a graph and you look at the slope, it means that if you're going faster, you have a steeper or a larger slope. So if I were to compare the 3 lines that I just put on this graph, the black car would be traveling faster than the blue car, and the blue car would be traveling faster than the red car. So what does it mean to go faster in terms of a graph? It means that you have a bigger slope. So larger slope. So who is driving faster, Jeff or Debbie? Well, it's Jeff, because he's traveling at 75 miles per hour and Debbie is only traveling at 60. How do we know? We calculated Debbie's slope or Debbie's rate.